Welcome back to my class in Spherical Trigonometry. For today, we will take up solution of oblique spherical triangles. Some of the methods used in solving oblique spherical triangles are also used in solving solution of oblique triangles in plane trigonometry, except that in plane trigonometry we only have one set of laws of cosine, while in spherical trigonometry we have two sets of laws of cosines. In plane trigonometry, an oblique triangle is described as one containing an obtuse angle. An obtuse angle is one whose measure is between 90 degrees and 180 degrees exclusive. That is, the measure of an obtuse angle is more than 90 degrees but less than 180 degrees. In spherical trigonometry, an oblique triangle is one that does not contain a 90-degree angle, or an oblique triangle is one that contains two 90-degree angle or three 90-degree angle. In solving oblique triangles in plane trigonometry, we solve for the unknown parts using the law of sines and the law of cosines. This is the law of sines that we use as one of the methods for solving oblique triangles in plane trigonometry. And the law of sines states that the ratios of a side to the sine of the opposite angle are equal. The triangle shown in the diagram is an example of oblique triangle. The angles, none of the angles is equal to 90 degrees. And the angle C is an obtuse angle. It is more than 90 degrees. While the angles A and B are acute angles. And the sides opposite A, B, C are small a, denoted by small a, small b, and small c respectively. The sine law, or the law of sines in symbols, is given by the equation sine of angle A over the side small a is equal to the sine of angle B over the side small b, and these two are equal to the sine of angle C over the side small c. The fraction sine of angle A over side small a is the side opposite angle A, is a ratio. Similarly, sine of angle B over side small b is a ratio. And sine of angle C over side small c is a ratio. And the law of sines says that these three ratios are equal. But this is not the law of sines that we will use in solving spherical oblique triangles. But the law of sines for solution of oblique spherical triangles is very much similar to this law of sines in plane trigonometry. Another method we use for solving oblique Spherical triangles in plane trigonometry is the law of cosines. The law of cosines states that the square of a side is equal to the sum of the squares of the two other sides minus twice the product of the two other sides and the cosine of the angle opposite the side. If we write the equation from the law of cosine for a, small a, the side opposite angle A, the law of cosine states that the square of a side, our side we consider is small a squared, is equal to the sum of the squares of the two other sides. The two other sides will be b, small b and small c. Hence, a squared is equal to b squared plus c squared minus twice the product of the two other sides. Twice means 2 times the product of the two other sides, b and c, and the cosine of the angle opposite the side. The side we are considering is small a, and the angle opposite the side is small a is angle A. Hence, for the side small a, we derive from the law of cosine the equation a squared equals b squared plus c squared minus 2bc times cosine of angle A. If you are considering side small b, the side opposite angle capital B, the two other sides will be small a and small c. And the angle opposite side small b is angle B. And so by the law of cosine, b squared is equal to a squared plus c squared minus 2ac multiplied by cosine of angle B. If we consider the side small c opposite the angle capital C, the two other sides are small a and small b. And the angle opposite small c is angle capital C. And by law of cosines, the square of c is equal to a squared plus b squared minus 2ab times the cosine of angle capital C. The triangle shown in the diagram is an example of oblique triangle. Although it does not contain an obtuse angle, it is an oblique triangle because none of the angles is a right angle. And this law of cosine is not the law of cosine that we will use to solve oblique spherical triangle. This law of cosine can be used only to solve oblique triangles in the plane or oblique triangles in plane trigonometry. To solve oblique spherical triangle, we use the following. Number 1, we use the law of sines. Number 2, we use the law of cosines for sides. Number 3, we use the law of cosines for angles. And these are the two sets of laws of cosines that I mentioned earlier. The law of cosines for sides and the law of cosines for angles. And number 4, we use the law of tangents in solving oblique spherical triangle. And the law of tangents are also known as Napier's analogies. We now state and give the formula for each of these four laws: the law of sines, the law of cosines for sides, the law of cosines for angles, and the law of tangents or Napier's analogies. There is a slight difference between the law of sines in plane trigonometry for solving oblique triangle in the plane and the law of sines in spherical trigonometry for solving oblique spherical triangle. In the law of sine in plane trigonometry, we have the ratio of a side to the sine of the angle opposite the side. In the law of sines, for solving oblique spherical triangle, we have a ratio of two sines: the sine of a side and the sine of the angle opposite the side. The law of sines for solving oblique spherical triangle states that the ratios of the sine of an angle to the sine of the opposite side are equal. And this law is stated and given in the following equation. We have the ratio of sine of side small a to the sine of the opposite angle capital A, and this ratio is equal to the ratio of the sine of side small b of the oblique spherical triangle to the sine of the angle opposite side small b angle capital B. And these first two ratios are equal to the ratio of the sine of the third side small c to the sine of the angle opposite small c, denoted by capital C. This is the law of sines for oblique spherical triangle, and we use this law depending on the parts of the oblique triangle given, which means that we cannot always use the law of sines to solve the unknown parts of the oblique spherical triangle. And in cases when we cannot use the law of sines, we have the law of cosines for sides, the law of cosines for angles, and the law of tangents or Napier's analogies. Another method that we can use for solving oblique spherical triangle is the law of cosines for sides. The law of cosines states that the cosine of a side is equal to the sum of the product of the cosines of the two other sides and the product of the sines of the two other sides and cosine of the angle opposite the side. We write the law of cosines for sides in symbols. We consider the spherical triangle shown in the diagram, and we start with side small a. If you are considering side small a, the other two sides will be side b, small b, and side small c. And the angle opposite the side small a is angle A. By law of cosines for sides, it says the cosine of small a is the product is equal to the sum of the product of the cosines of the other two sides, sides small b and c. And the product of the sines of the other two sides, small b and c, and cosine of the angle opposite the side. We are considering side A, the angle opposite. Side small, side A is angle A. Thus, by law of cosines for sides, cosine of small a equals product of cosine of side b, small b, and cosine of side small c plus the sine product of the sines of side small b and sine of side small c and the cosine of angle capital A. Now we consider the side small b. The other two sides will be side small a and side small c, and the angle opposite side small b is angle capital B. Again, by law of cosines, for sides, the cosine of b small b is equal to the sum of the products of the cosines of the two other sides, a small a and small c, and the product of the sines of the two other sides, small a and small c, and the cosine of the angle opposite the side, small b, which is angle capital B. Thus, by law of cosines for sides, cosines of small b is equal to cosine of small a multiplied by cosine of side small c plus sine of side small a times the sine of side small c multiplied by cosine of angle capital B. And the last equation for side small c, for side small c, the other two sides will be side small a and side small b, and the angle opposite side small c will be angle capital C. Again, by law of cosines for sides, cosine of side small c is equal to the product of the cosines of the two other sides, cosine of small a multiplied by cosine of side b plus the product of the sines of the two other sides, small a and small b, and cosine of the angle opposite side, small c, which is angle capital C. Hence, cosine of side small c is equal to cosine of side small a multiplied by cosine of side small b plus sine of small a multiplied by sine of small b multiplied by cosine of angle capital C. Again, we use the law of cosines for sides for solving oblique spherical triangle depending on the parts of the oblique spherical triangle given. Now, the law of cosines for angles is another tool for solving oblique spherical triangles. But this law can be used only depending on the parts given, which means that we cannot always use the law of cosines to solve oblique spherical triangle. And the law of cosines for angles states that the cosine of an angle is equal to the sum of the negative of the product of the cosines of the two other angles and the product of the sines of the two other angles and the cosine of the side opposite the angle. Using the law of cosines for angles, we can write three equations because there are three angles in an oblique spherical triangle. We start with angle A. If you are considering angle A, the two other angles will be angle B, capital B, and angle capital C. and the side opposite angle capital A is side small a. By law of cosines for angles, the cosine of angle capital A is equal to the sum of the negative of the product of the cosines of the two other angles, which are angle capital B and angle capital C, and the product of the sines of the two other angles, capital letters B and C, and cosine of the side opposite angle A, which is side small a. Thus, by law of cosines, cosine of capital A, angle capital A is equal to negative cosine angle capital B multiplied by cosine of angle capital C plus the sine of angle capital B multiplied by sine of angle capital C and the cosine of the angle opposite angle capital A, which is side small a. Now we write the equation for angle capital B from the law of cosine. If you are considering angle capital B, the two other angles are angle capital A and angle capital C. And the side opposite angle capital B is the side small letter b. Again, the law of cosines for angles states that the cosine of angle B is equal to the sum of the negative of the products of the cosines of the two other angles, angles capital letters A and C, and the product of the sines of the two other angles, capital letters A and C, and the cosine of the side opposite angle, capital letter B, which is side small b. Hence, cosine of angle B equals negative cosine of angle A, capital A, multiplied by cosine of angle C, capital C, plus sine of angle A, capital letter A, multiplied by sine of angle C, multiply by cosine of side small b, the side opposite the angle capital B. For angle capital C, the two other angles are angles A, capital A, and capital C. And the side opposite angle capital C is the side small letter c. Again, by law of cosines for angles, the cosine of angle C is equal to the sum of the negative of the product of the cosines of the two other angles, angles capital letters A and C, and the product of the sines of the two other angles, angles capital letters A and C, and cosine of the side opposite angle capital letter C, which is side small c. Thus, the equation for angle C is given by cosine of angle C is equal to negative cosine of angle A, capital A, multiplied by cosine of angle capital B, plus sine of angle A, capital A, multiplied by sine of angle B, capital B, multiplied by cosine of small side C. Small letter c is the side opposite the angle C. And those are the three equations containing cosines for the three angles of the oblique spherical triangle. Again, we use the law of cosines for angles depending on the parts of the oblique triangle, oblique spherical triangle given. Another device that we can use to solve oblique spherical triangle is the law of tangents. There is a law of tangents for solving oblique triangles in plane trigonometry. and to differentiate the law of tangents for solving oblique spherical triangles from the law of tangents used for solving oblique triangles in plane trigonometry. The law of tangents in spherical trigonometry is referred to as spherical law of tangents. And the spherical law of tangents is stated as a theorem. And to state the law of tangents, we let triangle ABC be a spherical triangle as shown in the diagram. A spherical triangle is a triangle on the surface of a sphere. And we let ABC be a spherical triangle on the surface of a sphere whose center is 0, point 0. Further, we let the sides small letters A, B, C of triangle ABC be measured by the angles subtended at the center of the sphere, point 0, where small letters A, B, C are opposite the angles, capital letters A, B, C, respectively. We now state the spherical law of tangents. The spherical law of tangents states that the ratio of the tangent of half the difference of two sides and the tangent of half their sum is equal to the ratio of tangent of half the difference of two angles opposite the sides and tangent of half their sum. To state the law of tangents in symbols, you take two sides of the oblique spherical triangle at a time. We start with the sides denoted by small a and small b, and the angles opposite these two sides, small letters A and B, are the angles denoted by capital letters A and B. And we start from the left-hand side of the equation that says the ratio of the tangent of half the difference of two sides. The difference of two sides is given by A minus B, and half the difference of these two sides is A minus B over 2. And that explains the denominator 2 at the left, in the numerator at the left hand side of the equation. A minus B over 2 is half the difference of the two sides. The two sides we are considering are sides small a and small b. And we take the tangent of half the difference of these two sides. We have tangent of a minus b over 2. In the denominator of the ratio, we have tangent of half their sum. Again, the two sides we are considering are sides small a and small b, and their sum is denoted by a plus b, and half their sum is a plus b over 2. And we get the tangent of half their sum. In the denominator at the left hand side of the equation, you see tangent of quantity a plus b all over 2. Thus, at the left hand side, we have the ratio of tangent of half the difference of the two sides, a and small b, tangent of a minus b or all over 2, and the tangent of half their sum, half the sum of the two sides we are considering a and b. And so in the denominator of the ratio at the left hand side of the equation, we have tangent of quantity a plus b all over 2. And this ratio is equal to, by the spherical law of tangents, is equal to the ratio of the tangent of half the difference of the two angles opposite the sides The two sides we are considering are small letters A and B, and the angles opposite them are capital letters A and B. And half the difference of these two angles is given by A minus B, capital A minus capital B all over 2. And we get the tangent of half the difference of these two angles. And the denominator in the ratio at the left-hand side of the equation is the tangent of half the sum of the two angles. The sum of the two angles is A plus B, and half the sum of these two angles is given by A plus B all over 2. And we get the tangent of half this sum of the two angles A and B opposite the sides small a and small b. Thus, at the left-hand side of the equation, we have the ratio of the tangent of a minus b all over 2 and tangent of quantity a plus b all over 2. The two sides and the two opposite angles opposite the two sides in the difference and sum must be taken in the same order. Thus, if you have a minus b, the difference of the sides a and b, you should have at the left-hand side of the equation the difference of angle capital A and angle capital B. If you have the difference of the sides A minus B at the right-hand side, you cannot have the difference of angle B minus angle A. The sides and the opposite angles must be taken in the same order when you write the equation from the spherical law of tangents. These are all the equations that can be written or derived from the spherical law of tangents. The last equation is the one we had as an example earlier, where we take the sides small a and small b. Now, these equations may be read from left to right or from right to left, as we did earlier, where at the left-hand side of the equation, we have the ratio of the tangent of half the difference of two sides and the tangent of half the sum of the two sides. And at the right-hand side, we have the ratio of the tangent of half the difference of the angles opposite the two sides and the tangent of half the sum of the angles opposite the two sides. But in these equations, we have the ratio of the tangent of half the difference of two angles and the tangent of half the sum of two angles. But as I said, you can always start from the right to the left or from the left to the right. If you are considering the angles B and C, capital B and capital C, the sides opposite these angles are denoted by small b and small c. And by the spherical law of tangent, if we are considering angles capital B and C, the ratio of the tangent of half the difference of angles B and C, denoted by tangent of 1/2 times quantity B minus C, and the tangent of half the sum of the angles B and C, denoted by tangent of 1/2 times quantity B plus C, is equal to the ratio of the tangent of half the difference of the sides opposite the angles capital letters B and C, which are small letters B and C, and the tangent of half the sum of the sides opposite angles capital letters B and C, which are small letters B and C. Hence, by the spherical law of tangents, the ratio of the tangent of 1/2 angles capital letters B and C and the tangent of half the sum of the angles B plus C is equal to the ratio of the tangent of half the difference of the sides small letters B and C, B minus C, and the tangent of half the sum of B and C, B plus C. Now, if you are considering the angles C and A, by the spherical law of tangents, the ratio of the tangent of half the difference of the angles capital letters C and A and the tangent of half the sum of these angles C and A is equal to the ratio of the tangent of half the difference of the sides opposite the angles C and A. And the tangent of half the sum of the sides C and A opposite the angles C and A. So if you are considering the angle C and A by the spherical law of tangents, the equation will be the ratio of the tangent of half C minus A, the difference of the angles C and A, and the tangent of half the sum of the angles C and A, C plus A, and this ratio is equal to the ratio of the tangent of half the difference of the sides small c and small a, and the tangent of half the sum of the sides small c and small a. You notice that the angles and the sides are taken in the same order. For example, in the first equation, you have angles B and C, capital letters B and C at the left-hand side. At the right-hand side, you also have the sides small b and small c in the same order. If at the left-hand side, you have the difference B, angle B minus angle C, you cannot have the difference of two sides at the right-hand side, C minus B. The angles and the sides, the opposite sides, should be taken in the same order when you write the equations from the spherical law of tangents. And the spherical law of tangents will not always apply when solving the oblique spherical triangles. You can only use the spherical law of tangents depending on the given parts of the spherical oblique triangle. Before I state Napier's analogies, another set of tools for solving oblique spherical triangles, let us state the law of tangents in plane trigonometry. This law of tangents is used to solve oblique triangles in the plane. And this law of tangents in plane trigonometry is not applicable for solving oblique spherical triangles. For the oblique spherical triangles, we use the spherical law of tangents. But we state the law of tangents in plane triangles so you can see the difference between the law of tangents in plane triangle and the spherical law of tangents. In plane triangle, the law of tangents states that the ratio of the difference of two sides to their sum is equal to the ratio of the tangent of half the difference of the angles opposite the sides to the tangent of their sum. The triangle shown in the diagram, the green triangle, is a oblique triangle because it does not contain a right angle. And the angles are denoted by capital letters A, B, C, and the opposite sides are denoted by small letters A, B, C respectively. If we are considering the sides, small letters A and B, and we write the equation from the law of tangents, we have the ratio of the difference of two sides denoted by small a minus small b, and their sum denoted by a plus b. At the right hand side of the first equation, you have a minus b over a plus b. That is the ratio of the difference of two sides to their sum, a plus b. And this ratio is equal to, by the law of tangents, to the ratio of the tangent of half the difference of the angles opposite the sides is small a and small b, and these angles are angles A, capital A, opposite small a, and angle capital B opposite small b. At the left hand side, we have the ratio of the tangent of half the difference of the angles opposite the two sides. That is tangent of quantity A minus B over 2, where a minus b over 2 is the half of the difference of the angles A and B opposite the sides small a and small b, and the tangent of half their sum. Half their sum is given by a plus b over 2. Thus, by the law of tangents, we have in the first equation, if we are considering the sides small a and small b, the ratio of the difference of two sides a minus b and their sum a plus b is equal to the ratio of the tangent of half the difference of the angles opposite the sides small a and small b, and the tangent of half their sum. The sum a plus b divided by 2, that's half the sum of the two angles a and b opposite a minus b. And you can see the pattern from these three equations. If you are considering the two sides small b and small c, and you write the equation from the law of tangents, you have the ratio of the difference of the two sides, b minus c, and their sum, b plus c. That ratio is written as b minus c over b plus c, and that ratio is equal to the ratio of the tangent of half the difference of the angles opposite the sides, small b and small c, and these angles are angle capital A and angle capital C. And half their sum is denoted by b minus c over 2, and half their difference is denoted by b minus c over 2, and half their sum is denoted by b plus c. And at the left hand side, you have the ratio of the tangent of half the difference of the two angles opposite the two sides, and the tangent of half the sum of the two angles opposite the two sides. Thus, if you are considering the two sides small b and small c, by law of tangents, the ratio of the difference of the two sides b minus c and their sum b plus c is equal to the ratio of the tangent of half the difference of the angles opposite the two sides. Half the difference of these two angles is given by b minus c over 2, and the tangent of half their sum. The half their sum is given by b plus c over 2. If you are considering the sides c and a, and you write the equation from the law of tangents, the ratio of the difference of the sides c and a, c minus a, and their sum, c plus a, is equal to the ratio of the tangent of half the difference of the angles opposite c and a, the angles capital C and capital A, and half their sum, half their difference is given by c minus a over 2. And the tangent of half their sum, half the sum of the two angles opposite the sides small a and small c, is given by c plus a over 2. Thus, if you are considering the sides c and a, The equation from the law of tangents is given by the ratio of the difference of the two sides C and A, C minus A, and their sum C plus A, and this ratio is equal to the ratio of the tangent of half the difference of the two angles and the tangent of half the sum of the two angles. Again, this law of tangents is for solving oblique triangles in the plane. And this is not applicable for solving spherical oblique triangles. We now state the Napier's analogies. Napier's analogies consist of four equations containing the tangent function. That is why Napier's analogies are also known as the law of tangents. We let triangle ABC be a spherical triangle as shown in the diagram. It is a triangle on the surface of the sphere, on the surface of a sphere whose center is point 0. We let sides small a, small b, and small c of triangle ABC be measured by the angles subtended at point 0, where A, B, C, small letters A, B, C are opposite the angles capital letters A, B, and C respectively. This is the first of the four of Napier's analogies, known as tangent of half the sum of two sides. The two sides in this equation are side small a and small b. And Napier's analogies say that the tangent of half the sum of the two sides is equal to the ratio of the cosine of half the difference of the two angles opposite the two sides. Angle capital A is the angle opposite the side small a, as we see in the diagram earlier. Angle capital B is the angle opposite the side small b. And the cosine of half the sum of the two angles, capital letters A and B, opposite the sides small a and small b, multiplied by the tangent of half the third side. If you are considering the sides A and B, the third side is C. Hence, the tangent of half the sum of two sides by Napier's analogy is given by this equation. The tangent of half the sum of two sides is equal to the ratio of the cosine of half the difference of the angles opposite the two sides, and the cosine of half the sum of the two angles opposite the two sides, multiplied by the tangent of half the third side. Now, you can also write the equations for half the sum of the sides A, small a, and small c. And you can also write the equation from the tangent of half the sum of the sides B and C. If you write the equation for the tangent of half the sum of sides small a and small c, you should get tangent of A plus C over 2 equals cosine of capital A minus capital C over 2 over cosine of A plus C over 2 multiplied by tangent of small b over 2. That is the tangent of the sum of half the sum of two sides is equal to, that is the tangent of half the sum of the sides A and C is equal to the ratio of the cosine of half the difference of the two angles opposite sides small a and small c. A minus C over 2 over cosine of half the sum of the two angles opposite the side small a and small c, A plus C over 2 multiply by tangent of the third side. If you are considering sides A and C, the third side will be B, tangent of small b over 2. So for the side small a and small b, tangent of A plus C over 2 equals cosine of A over A minus C over 2 over cosine of A plus C over 2 times tangent of small b over 2. This will give us the second equation of the four Napier's analogies. It's called the tangent of half the difference of two sides. Earlier we have the tangent of half the sum of two sides. Now if you are considering the side small a and small b, the tangent of half their difference, tangent of a minus b over 2 by Napier's analogies is equal to the ratio of the sine of a minus b over 2, sine of half the difference of the angles opposite the sides small a and small b, and sine of half the sum of the angles opposite sides small a and small b multiplied by tangent of half the third side. If we are considering the side small a and small b, the third side will be small c. Hence, by this tangent of half the difference of sides, two sides, the tangent, if we are considering the side small a and small b, the tangent of half their difference, a minus b, is equal to the ratio of the sine of half the difference of the angles opposite the side small a, small b, which are angles capital A and capital B, and the sine of half the sum of the two angles opposite the side small a, small b, again denoted by capital A and capital B, multiplied by tangent of half the third side, which is small c. You may try to write the equation for the tangent of small a minus small c over 2. And there is a pattern evident from this equation. You can also write the equation for tangent of b minus c. If you are considering the sides b and c, the third side will be a. The third of Napier's analogies is given by this equation using angles capital A and capital B, and this is known as tangent of half the sum of two angles. In this equation, the two angles considered are angle A, capital A, and angle B, capital B. And Napier's analogy says that the tangent of half the sum of two angles is equal to the ratio of the cosine of half the difference of the two sides opposite the two angles, and the cosine of half the sum of the two sides opposite the two angles multiplied by cotangent of the third angle. Cotangent of half the third angle. If you are considering angles A and B, the third angle is angle capital C. Again, the angles and the sides are taken in the same order. If you consider the two angles A and C, then by Napier's analogy, the tangent of half the sum of A and C, tangent of A plus C over 2 equals cosine of small a minus small c over 2 over cosine of small a plus small c over 2 multiplied by cotangent, and the third angle will be angle B, cotangent of capital B over 2. You can also try to write the tangent of B plus C, the tangent of half the sum of angles B and C, tangent of B plus C over 2. By Napier's analogy, the tangent of b plus c over 2 should be equal to cosine of b minus c over 2 over cosine of b plus c over 2, small letters b plus c over 2, multiplied by cotangent of angle capital A over 2. If you want the tangent of b plus a over 2, then it should be equal to cosine of small b minus small a over 2 over cosine of small b plus small a over 2 multiplied by cotangent of half of angle C, cotangent of capital C over 2. Again, the angles and the sides should be taken in the same order. This is the fourth and the last of Napier's analogies, and it is called the tangent of half the difference of two angles. Again, in this equation, angles A and B are considered, and the third angle is angle C, capital C. And by Napier's analogy, the tangent of half the difference of A minus B is equal to the ratio of sine of A minus B over 2, where small a and small b are the sides opposite the angles capital A and capital B, over sine of half the sum of the two sides opposite angles A and B, A plus B over 2, multiplied by cotangent of half the third angle, which is angle C. Again, by Napier's analogy, the tangent of A minus B over 2, that is tangent of half the difference of two angles, is equal to the ratio of sine of half the difference of the two sides opposite the two angles and sine of half the sum of the two sides opposite the two angles multiplied by cotangent of half the third angle. If you want to write the tangent of A minus C over 2, or tangent of the difference, half the difference of sides A and C, tangent of A minus C over 2 should be equal to sine of A minus C over 2, small letters, over sine of A plus C over 2 multiplied by cotangent of half the third angle, and the third angle will be angle capital B. If you want the tangent of B minus C over 2, tangent of B minus C over 2, by Napier's analogy, should be equal to sine of small b minus small c over 2 over sine of small b plus small c over 2 multiplied by cotangent of the third angle, angle capital A over 2. As I said earlier, the formula that you will use, whether you will use the law of sine or law of cosines for sides or law of cosines for angles, law of tangents or Napier's analogies, depend on the three parts of the oblique spherical triangle given, and these are the six possibilities. The three parts may be given. In case 1, two sides and included angle are given. That is, included angle is the angle between the two sides. Case 2, two angles and the included side are given. The included side is the side common to the two angles. Case 3, two sides and an angle opposite one of them are given. Case 4, two angles and a side opposite one of them is given. Case 5, three sides are given, and the last case, three angles are given. We will have examples for cases 1, 2, 3 for today's lesson. Our example 1 is Our example for case 1, where the given are two sides and the included angle. As shown in the oblique spherical triangle, shown the angle given is angle B, 114 degrees 53 minutes. And the two sides given are small a, side is small a, 106 degrees 25 minutes, opposite angle capital A, and the side is small c, 42 degrees 16 minutes, opposite angle capital C. And angle capital B is the angle between the sides small a and small c, and it is called the included angle. And to solve this oblique spherical triangle is to find the parts that are not given, angle A, angle C, and small side B opposite angle B. We start by finding the side small b by law of cosine for sides, because the two other sides are given, small a and small c, and the angle opposite is small side b, angle capital B is also given. By law of cosines for sides, cosine of small b is equal to the product of the cosines of the two other sides, cosine small a, cosine small c, plus the product of the sines of the two other sides, and cosine of the angle opposite side is small b. That is plus sine small a, sine small c, multiplied by cosine angle b. And we substitute the values. Small a is 106 degrees 25 minutes, small c is 42 degrees 16 minutes, and angle capital B is 114 degrees 53 minutes. After substitution, we have cosine small b equals cosine of 106 degrees 25 minutes multiplied by cosine of 42 degrees 16 minutes plus sine of 106 degrees 25 minutes multiplied by sine of 42 degrees 16 minutes multiplied by cosine of 114 degrees 53 minutes. And therefore, B is equal to shift cosine or arc cosine of cosine 106 degrees 25 minutes multiplied by cosine of 42 degrees 16 minutes plus sine of 106 degrees 25 minutes multiplied by sine of 42 degrees 16 minutes multiplied by cosine of 114 degrees 53 minutes. And using your calculator, in degrees, you should get 118.725389736 degrees. To convert the answer to degree, minutes, and second, just press in your calculator the key with degree, minutes, and seconds. And you should get the final answer for side small b, 118 degrees, 43 minutes, and 31.40 seconds. Since we are given angle B and we have found the side small b by law of cosines for sides, and we are given the side small a, we find angle A by law of sines. That says the ratio of the sine of angle A to the sine of the opposite side small a is equal to the ratio of sine of angle B to the sine of the opposite side small b. And to this equation, we substitute the values. Small a, 106 degrees 25 minutes. Angle capital B is given 114 degrees 53 minutes. And we have solved for side small b, 118 degrees 43 minutes, 31.40 seconds. And we get sine of A over sine of 106 degrees 25 minutes equals sine of 114 degrees 53 minutes over sine of 118 degrees 43 minutes 31.40 seconds. Now cross multiply sine 106 degrees 25 minutes by sine of 114 degrees 53 minutes. And you get sine A equals sine of 106 degrees 25 minutes multiplied by sine of 114 degrees 53 minutes over sine of 118 degrees 43 minutes and 31.40 seconds. Thus, angle A is equal to shift sine or arc sine or inverse sine of sine of 106 degrees 25 minutes multiplied by sine of 114 degrees 53 minutes over sine of 118 degrees 43 minutes 31.40 seconds. You may compute for A directly in your calculator, or if you choose to compute the values of sine one by one, take all the decimal numbers and round off only in the final answer. And you should get angle A equals 82.8862777987 degrees. An important note in solving oblique spherical triangles, the angle and its opposite side must terminate in the same quadrant. In our example, angle A, we obtain 82.8862777987 degrees, but its opposite side, small a, which is given, is 106 degrees 25 minutes. So the angle A that we get does not terminate in the same quadrant as the given small side A, 106 degrees 25 minutes. Thus, we take the supplement of 82 degrees, we subtract 82.8862777987 from 180 degrees. And you should get A equals 97.11372201 degrees. And this angle 97 terminates in the same quadrant, which is second quadrant, as the side small a, 106 degrees 25 minutes. And to convert the answer to degree, minutes, and second, again, you press in your calculator the key with degree, minutes, and second. And you should get the final angle A equals 97 degrees 6 minutes and 49.40 seconds. And finally, to find angle capital C, we use the law of sines because we are given the small side C and we are given the angle capital B, and we have found the side small b. So you can use the equation sine of capital C over sine of side small c equals sine of angle B over sine of B. Or you can use the equation sine of angle capital C over sine of small c equals sine of angle A over sine of side small a, because we have already solved for angle A. Using the first equation, sine of angle C over sine of side C equals the ratio of sine of angle B, and sine of small b, we substitute the values. Small c equals 42 degrees 16 minutes, angle B 114 degrees 53 minutes, and side small b 118 degrees 43 minutes and 31.40 After the substitution, we get the equation sine capital C over sine of 42 degrees 16 minutes equals sine of 114 degrees 53 minutes over sine of 118 degrees 43 minutes 31.40 seconds. Again, we multiply sine of 42 degrees 16 minutes by sine of 114 degrees 53 minutes, and you should get sine C equals sine of 42 degrees 16 minutes multiplied by sine of 114 degrees 53 minutes over sine of 118 degrees 43 minutes and 31.40 seconds. Thus, angle C equals inverse sine or shift sine of 42 degrees 16 minutes sine multiplied by sine of 114 degrees 53 minutes divided by sine of 118 degrees 43 minutes and 31.40 seconds. And using your calculator, you should get angle C equals 44.088612766 degrees. Again, to convert the answer to degree, minutes, and seconds, press in your calculator the key with degree, minutes, and seconds. And the final answer for angle C equals 44 degrees, 5 minutes, and 19.01 seconds. The given small c or side C is 42 degrees, 16 minutes, and the angle capital C that we get 44 degrees, 5 minutes, and 19.01 minutes both terminate in the same quadrant or first quadrant. So there is no need to take the supplement of angle capital C. Our next example is for case 2 where the given are two angles and the included side. Solve the spherical triangle with the given side small c 113 degrees. The two angles given are capital B 66 degrees, angle A capital A 110 degrees. And the side small c is the side common to the two angles A and B, and it is called the included side. We start with the law of cosines for angles to find the angle capital C, since the two other angles are given, angle A and angle B, and the side opposite angle C is also given, small c 113 degrees. So we find angle C by law of cosines for angles. And by law of cosines for angles, cosine of angle C equals the negative of cosine of angle A multiplied by cosine of angle B plus the product of the sines of the two other angles, sine of angle A multiplied by sine of angle B multiplied by cosine of the side opposite angle C, small c. And to that equation, we substitute the values. Small c equals 113 degrees, angle B 66 degrees, and angle A 110 degrees. After the substitution, you should get the equation cosine of angle C equals negative cosine of 110 degrees multiplied by cosine of 66 degrees plus sine of 110 degrees multiplied by sine of 66 degrees multiplied by cosine of 113 degrees. Thus, angle capital C equals shift cosine of negative cosine of 110 degrees multiplied by cosine of 66 degrees plus sine of 110 degrees multiplied by sine of 66 degrees multiplied by cosine of 113 degrees. And using your calculator, you should get angle C equals 101.321363422 degrees. And you check the given small angle C. The small side C opposite angle capital C is 113 degrees. And the angle capital C 101 degrees and the opposite side small c 113 degrees terminate in the same quadrant, which is the second quadrant. Thus, there is no need to get the supplement of C. Thus, the final answer, angle C in degree, minutes, and seconds should be 101 degrees, 19 minutes, and 16.91 seconds. Now we find the side small a by law of sines. Since we are given angle A, we are given the side small c, and we have found the angle capital C. We find A by law of sines, the ratio of sine of small side A, and the sine angle A is equal to the ratio of the sine small side C and the sine of the opposite angle capital C. We substitute A equals 110 degrees, capital C 101 degrees, 19 minutes, and 16.91 seconds, and the given side is small c 113 degrees. After the substitution, we get the equation sine of small a over sine of 110 degrees equals sine of 113 degrees over sine of 101 degrees, 19 minutes and 16.91 seconds. We multiply sine of 110 degrees by sine of 113 degrees. We get the equation sine A equals sine of 110 degrees multiplied by sine of 113 degrees over sine of 101 degrees, 19 minutes and 16.91 seconds. The small a equals shift sine of 110 degrees multiplied by sine of 113 degrees over sine of 101 degrees, 19 minutes, 16.91 seconds. And using your calculator, you should get a small a equals 61.9036713167 degrees. But the given angle capital A is 110 degrees, which terminates in the second quadrant. But the small side A that we get is 61.90 degrees that terminates in the first quadrant. Thus, we should take the supplement of small a by subtracting 61.9036713167 degrees from 180 degrees, and you should get 120.096326868 degrees. Now 110 degrees angle A and 120 degrees for small a now terminate in the same quadrant, second quadrant. Pressing your key in your calculator for degree, minutes, and second, the final small a is 120 degrees, 5 minutes, and 46.78 seconds. Finally, we solve for the side small b by law of sines. You can either use the first equation or the second equation. In the first equation, we have the ratio of sine of small b to the sine of the opposite angle capital B equals the ratio of sine small a and the sine of the opposite angle capital A. Or you can use this equation, sine of small b and sine of the opposite angle capital B is equal to the ratio of the sine of small c and the sine of angle capital C. Using the first equation, sine of small b over sine of angle B equals sine of small c over sine of angle capital C, we substitute the values. Capital B equals 66 degrees. Angle capital C, 101 degrees, 19 minutes, 16.91 seconds. And side small c, 113 degrees. After the substitution, we get the equation sine small b over sine of 66 degrees equals sine of 113 degrees over sine of 101 degrees, 19 minutes, 16.91 seconds. Again, we multiply sine of 66 degrees by sine of 113 degrees. We get sine small b equals sine of 66 degrees multiplied by sine of 113 degrees over sine of 101 degrees, 19 minutes, 16.91 seconds. Hence, angle B, small b equals arc sine or shift sine or inverse sine of 66 degrees multiplied by sine of 113 degrees over sine of 101 degrees, 19 minutes, and 16.91 seconds. And using your calculator, you should get 59.0493753124 degrees. And press the key in your calculator with degree, minutes, and seconds. And the angle side B in degree, minutes, and seconds, you should get 59 degrees, 2 minutes, and 57.75 seconds. For your practice, please try the following exercise. This exercise is for case 1. The given are two sides and the included angle. Solve the following oblique spherical triangle given that small b equals 156 degrees 12 minutes, small c 112 degrees 48 minutes, and the included angle capital A 76 degrees 32 minutes. The law of tangents for spherical triangles was described in the 13th century by Persian mathematician Nasir al-Din al-Tusi, who also presented the law of sines for plane triangles in his 5-volume work Treatise on the Quadrilateral. Nasir al-Din al-Tusi is considered as the father of spherical trigonometry. And that completes our lesson for today. Thank you for joining me in my class today in spherical trigonometry.
Are you not entertained?